In this video, we're going to be taking a look at the net electric field. We're going to be taking a look at three different scenarios, one with a single charge, one with two charges, and then the final one with three charges, which is going to be the most complex. So for each of these, what you're going to do to find the electric field is you're going to use the formula KQ over R squared, where K is the constant, 9 times 10 to the ninth, Q is the charge, and then the R is the separation distance. That's always squared in the denominator. And then when you solve for the electric field, that is how many newtons per coulomb are being applied to anything at that specific distance. So the first one, we have something at 3 microcoulombs. So if we take the constant K, 9 times 10 to the ninth, times the Q value, which is 3 times 10 to the negative sixth, and then we divide it by the R value squared, which is this distance of 2, then we will get our electric field, which is 6,750 newtons per coulomb. So that one is going to be the easiest case, obviously, because we only have one charge. And these cases over here, we have two different charges. So with a positive charge and a negative charge, you want to make sure you consider the direction. So we're going to go ahead and solve for the magnitude of each of these electric fields, and then we're also going to solve for the final net electric field once considering the directions as well. All right, now that we've solved for the electric field for both of those charges, we have 27,000 and 4,500 newtons per coulomb. Now remember, the direction of the electric field is based on a positive test charge. So if we're at this little star over here, it's going to be pushed to the right. It's going to be repelled from this positive Q, and then it's going to be attracted towards this negative because the electric field lines are always moving towards a negative charge. So this little position right here where the star is would be directed towards the right. So the red charge is repelling the object to the right, and then the blue charge is attracting it to the right. So they're working together. So the net electric field is going to be the sum of these two. And then if you go ahead and add those up, then you have a total of 31,500 newtons per coulomb to the right. And then if we also want to add the direction to our first answer, this was a positive Q value, so that's going to be pointing away from the object towards the star, so that'd be to the right. So let's do a very quick summary for these first two problems before we get into the last one, because it's going to be a little bit more difficult. So this one is just plugging straight into the formula KQ over R squared. Once you have multiple charges, you want to pay attention to their direction. And if they're all along the same line, then basically what you're going to do is add or subtract them based on if they are pointing in the same direction or opposite directions, and then that will give you your final answer. So let's go ahead and clear these out and work on the last problem. Now for our last problem, if we're focusing on this position right here, we have the separation distance and the value of the Q for the purple charge. Same thing for the red one. The blue one we do not. So we want the diagonal distance across here. And we can do that a few different ways. You can say that for an isosceles triangle, this side over here is going to be 2 root 2. Or you could use Pythagorean theorem, a squared plus b squared equals c squared, and then do 4 plus 4, and then add those up to get 8, and then the square root of 8 is 2 root 2. Okay, now we have our separation distance for the blue charge as well. So let's go ahead and find the E field for all three of these, and then we're going to use those 3 E fields to get one final net E field. Now we found our three electric fields that are coordinated with the color of the charge, red, blue, and purple. Now the part where it gets a little bit more complex is taking a look at the blue charge because its electric field is acting on an angle. So let's take a look at the red and purple one first. So the red one is a positive charge, so the electric field is pointing away from it, which means it's going to be pointing to the right. And then for the purple one, it is also positive. So this is going to be pointing away from it. So this is going to be pointing upwards. And for our final electric field of 2,250, that one is going to be pointing towards it. So it's going to be pointing towards the -2 microcoulomb charge this direction. Now it's going to be on a 45-degree angle because we are splitting this 90-degree angle. So it's going to be 45 degrees on either side. So what we're going to do is I'm going to go ahead and draw a little separate triangle on the side where we have a 45-degree angle here. And then we have a y component and an x component. And then the hypotenuse of the triangle is that electric field of 2250. So if we wanted the adjacent side, we could do the cosine of 45 degrees times 2,250. And then that's going to give us the vertical component going downwards, which is going to be rounded off to 1,591. And then because it's a 45-degree angle, I don't necessarily have to do the math again, but it would be sine of 45 degrees times the 2250, which would also equal 1,591 as well. So we have two more electric fields to consider. We have this component over here, 1,591 downwards, and then we have 1,591 to the left. So let's go ahead and take a look at all of our electric fields along the two different axes. So let's take a look at everything along the x-axis. Everything along the x-axis would be this, the 6750 to the right, and then the 1,591 to the left. So since they're in opposite directions, we are going to subtract them. And then that's going to leave us with a final horizontal electric field of 5,159 newtons per coulomb to the right. Now for our y values, everything in the vertical direction, we have 9,000 newtons per coulomb directed upwards. And then we have 1,591 down. So we're going to subtract that because it's in the opposite direction. And then that's going to give us 7,409 newtons per coulomb. And then that's going to be directed upwards. Now, anytime you have a vertical and a horizontal and vertical component, you're going to want to add them up as vectors with the tip to tail method. So we're going to go over to the right, 5,159 newtons per coulomb. And then we have a vertical component, which should be longer, but it's 7,409. And then our final resultant vector is right over there. So if we go ahead and use the Pythagorean theorem, then it would be a squared plus b squared equals c squared, which is basically just square rooting both sides to get your value. And then we'll get our final component of our triangle, which equals 9,028.2. Now that is our final net electric field. In addition to that, because it's a vector, we're going to go ahead and find this angle theta right over here. So you could use any inverse trig function you would like. I'm going to go ahead and take the inverse tangent of the opposite end, 7409, divided by the adjacent end, 5159. Put that in my calculator, and that's going to give me a final angle of 55.15 degrees. So when working out a problem like this, you're going to want to do the KQ over R calculations first, and then go ahead and find those electric fields. Now, because those are all vectors, you definitely want to pay close attention to whether they're positive or negative charges to see whether the E fields go towards or away, and then kind of tag each of those different things with an arrow, either on your actual diagram over here or off to the side, either one. If you have anything on an angle, be sure to break it up into X and Y components with a little triangle, as I did over here in blue. And then once you sum up all of those things, which would either be adding or subtracting them, then you're going to have your final horizontal and vertical components. Once you have your final horizontal and vertical components, like I do in purple over here, you're going to piece those together with the tip to tail vector addition method, get a final resultant vector. That final resultant vector is going to be your net E field with all of your charges combined, which is our final answer in orange over here. And then if you would like to find the angle at which it's directed, then you're going to go ahead and use an inverse trig function of any sort. Just want to make sure that you find the correct sides of the triangle, and then you have your angle. So I hope that was helpful to you. Thank you for watching and listening.